Section 6.2 is on using the normal distribution, and from the last section we had the notation x is distributed normally with a mean mu and a standard deviation sigma. That's the notation. I've got Mo Manu here. He was chasing his tail on the floor, so I had to pick him up for a second. So what we're going to do is connect the idea of the distributed, the normally distributed continuous random variable. We're going to connect that to probability in a way that ends up being very powerful for statistics. So to start with, I'm going to draw a normal curve and then pick out, I don't know what to call it, I'm just going to call it x because it's an x value. It's not the variable, it's just some number here. The mean, of course, is right in the middle. The standard deviation tells us how wide this is spread. This x value is going to separate the area on the left underneath the curve from the area on the right. Well, I'm shading the area on the left under the curve. That's the one that I want to focus on first. The shaded area is equal to the cumulative probability as a function of x. So remember, cumulative, we add up all the smaller probabilities to get the cumulative probability. In the notation we'll use, this is the probability that the random variable itself, the main character here, is less than this value of x. So the probability that x is less than x, it doesn't make very much sense to say it, but it means the probability that a randomly selected individual will be less than or equal, no, less than it says here, less than this x value. And you can see this is less than half of it, so that's a lower probability, less than 0.5. Let's also look at the total area under the curve equals, since it's a probability distribution, that area is 1 for the total area, a probability of 1 for the whole thing, or 100%. So if I take the probability that x is less than that little value of x, plus the probability that x is greater than that little value x, that's the whole thing. That's everything. That equals 1. And to demonstrate that, I should have kept my picture up there, but it was like this, with this x value and this shading over here. So the probability that x is less than this little x value is represented by this area. And the probability that the variable is greater than that value is represented by this area. And if I put them both together, it adds up to 1, because that's the whole area under the curve. This equation can be rearranged to give the probability that x is greater than x is equal to 1 minus the probability that x is less than x. So I'm just subtracting this from both sides here, really. But this is the complement rule, or the formula for the probability of a complement. And you can see how these two regions, the shaded region and the white region, complement each other in the sense of probability. Another aspect of probabilities with the normal distribution is that the probability that x is less than or equal to a particular x value is the same as the probability that the variable is less than. So that or equal there, that or equal to, doesn't matter. The reason is, I'm going to draw this sketch again, but only for this one value of x. Think about the piece right here, under the curve, above the x value, but with no width, just that one little line segment. The area of that line segment is 0. The probability that the variable is exactly equal to that number is 0 because it has no area. Sometimes they call it a degenerate rectangle. It's got a height but no width, or 0 width. I've got a numerical example to demonstrate this about the area to the right and the area to the left. And I'll draw a picture when I'm done, but I just want to say as an example, if area to the left is 0.2, .0228, then area to the right is 1 minus 0.0228, or 0.9772. And for this picture, the area to the left is a very small probability. That's 2%, or 2.2, it's a little over 2%. This is a little over 97%, or almost 98%. This picture that I'm going to draw is going to have a very, very little area to the left of my x value, and a big area to the right. So this is this number, 2.28%, and this one, this area is 97.72%. The area to the left is the small one. The area to the right is the larger one. I have another example about test scores. That says, this is example 6.8 in the text. Exam scores in an algebra class were normally distributed, normally distributed with mu equals 63 and sigma equal to 5. So the mean is 63, that's the average score. It doesn't say it's out of 100, but it'd be low, but whatever. The spread of the data is described by the standard deviation, how wide the curve would look. Of course, it's got to have an area of 1, so if it's wider, it has to be lower. If it's narrower, it has to be taller. And you can see a variety of normal distributions in the pictures in the text. So for this problem, to start with, we're going to find the probability that a random student scored over 65. So that is above average. We're going to find the exact probability by using this. So the x variable, I'm going to make a couple notes about that. The continuous random variable x represents an exam score, or one single randomly selected exam score. This randomly selected exam score. We know from the given information that x is distributed normally, it says there, with a mean 63 and a standard deviation 5. And that's how you use the notation. I'm just putting in the numbers. It's always the mean and then the standard deviation. And now I'm going to draw a picture. So I want to leave my question up, but all this stuff in the preamble, I've got that right here. That whole sentence summed up to this notation. I do want to draw the picture to guide me. We're going to actually use the calculator more than drawing the picture, but it is still a very good guide. So 63 is the mean, and 65 is the score of interest. Find the probability that the random student scored over 65. That means greater than 65. This is the region I'm interested in. And what we're going to look for is this area, the area that I've shaded. That's the probability that, I'm just going to call it X instead of that capital X thing. We're using numbers in this case, so we don't have to have the fancy X. There's only one X. It's not capital X and little x. It's just the probability that that random score, randomly selected score, is greater than 65. And that's the probability notation for what we're going to compute here. The probability that the score, or X, is greater than 65. So, I have it. I just don't have room to write it. First, I'm going to write it down so we can discuss the meaning of it. But the probability that X is greater than 65 is 0.3446. So where did I get that number? It's on the paper. But we used to have to find the z-score for 65. Then look up the table of z-score, whatever that z-score would be. Areas are, it would give us this area. Then we could use that complement rule, do 1 minus this area to get this area that we're looking for. So it was complicated. You would use a calculator, probably, but not a calculator that has statistics functions. TI-36 and TI-83, TI-84 have functions where we don't have to actually get into the z number here. First, for the TI-36, you're going to use the second function. So it's the second button. And then choose the stat regression / distribution menu item. The key is labeled data. But above it, this is what it is because it's for statistics, regression, and distributions. We're using a distribution in this case. So you want to choose DISTR from that menu. The next step, 2 is the shortcut button, or you can scroll down to it to get to this menu item. It's number 2, and it's called normal lowercase CDF. So normal CDF is the item you want. It's going to give you kind of an input menu that says put in the mean. In this case, the mean is 63, so I would put in the 63. And then the standard deviation, sigma, is 5. And the lower bound in this case, we're talking about the bounds for this shaded region. The lower bound is 65. And I don't have space to write this. I'm going to have to go back up to the top. we're really done with the picture. It's this thing that we're trying to evaluate, and you should get this number if you do it correctly. The area there was 34% of it, or 0.3446. So the last piece you'll need here is the upper bound. And that shaded region keeps going to the right all the way down the x-axis, all the way down the number line. So it's really, we need to put in infinity, but that's not a number. That's just kind of like the direction. The number you should use, or the number I use, I press 1 exponential notation 99. This means 1 times 10 to the 99th. And this button right here may appear as a double capital E. This is the scientific notation. This is the number in front, and this is the exponent on the 10. So it's equal to 1 times 10 to the 99, but it's faster to type it like this than it is like this. You really could just put 10 to the 99th in this case. It's equal. All right, the other thing about this, and this applies to the TI-84, TI-83 also, the exponential notation. For this one, this part and then this last step is all you need. Press enter, or calculate, I think is the menu select item, and it'll give you this number if you do all these steps correctly. I want to go through the steps now for the TI-83 or TI-84 and the menu items that they have. You can also find things like this, guides on the internet. If you search for a PDF, it'll be an easy file for your computer to read. But yeah, you can find it using your calculator's name and what you're trying to do, which is normal CDF, normal cumulative distribution function is what that stands for. Let's see. A little more on the scientific notation later, but let me quickly write up the commands for the TI-84 is what I have. So the second function is what it starts with. Then the DISTR key, which is on the vars, or for variables key, but it's this function. The second vars is the distributions. The second menu item is normal CDF, and what it's going to do when you click this, it's going to print onto the home screen the normal CDF function. Well, that stands for function, so it's the normal cumulative distribution function. For the TI-84, possibly TI-83, it might be a menu style like the other one, but it's the same commands. What I need to put in are the 65, which is the lower bound. That goes in first. Then my upper bound, remember 1E99, gives me a very, very large number that's effectively infinite. And then, so that's the upper bound. And then the mean. So the mean was 63. I'm just going to label that with mu. The mean was 63. And finally, the standard deviation, which was 5. And you can close the parentheses. That's what it's meant to have, is a closed parentheses with these 4 input parameters. We did the same thing with the TI-36 things, but it was one input in it at a time in a menu. This is all in one function. And it's a great way to write it if you can remember that they need to be in the order lower, upper, mu, sigma. All right. And then this should give you that same number, 0.3446. So try this with your TI-84 or TI-83. Make sure you can find the normal CDF. and input these, they have to be in this order. Now, if we're trying to find an area, let me do a little sketch to point at. If we're trying to find an area to the left, let's say, all this area. If I'm trying to find an area to the left of a particular value, I'm going to call it K. That way I don't have to fool around with two different X's. This area, with a mean of mu and a standard deviation of sigma, whatever that is, I can find the area to the left in the following way. It's the normal CDF. Lower bound in this case is negative infinity. I can use the same notation I did before, E, but have a negative sign in front of it. So it's really all the way down the number line that way is my left bound. My right bound here is K. My mean is whatever mean is in standard deviation. This is the computational version of negative infinity. It's not really equal to negative infinity, but it's such a large negative number that for the purposes of the normal cumulative distribution function, it's negative infinity. Okay, so that same example, I'm going to write the summary, and we've had a chance to see what some calculator functions are. But for the second part of that example, remember the test scores are distributed normally with a mean of 63 and a standard deviation of 5. And in this case, we want to find the probability that a random test score is less than 85. So different situation in a couple different ways. Different test score for one thing, that's our bound, or one of our bounds. But also less than instead of greater than. I'm going to draw the picture to guide my reasoning for this. Remember, the mean is right in the middle. In this case, I know it's 63. It's a little harder to interpret the 5, but the place where these things start to switch back from a downward curve to an upward curve, that's one standard deviation. So that would be 5. This would be 68 right here, and this would be 58. Anyway, here though, we're trying to find what's the probability that the score is greater than, nope, less than, less than 85. It's very likely that it's less than 85. You can see most of the area under the curve is shaded because it's over here. 85 is to the right of 63. I can calculate this with the normal CDF, and I'm going to label these a little bit differently. You might want to do it this way. It's shorter. My lower bound in this case is negative 1E99. My upper bound is 85. That's the right end of this region. My mean is 63, and my standard deviation is 5. That comes out to 0.999994583. That's too many digits to write. Don't write out like 5 digits. You get the idea. This is so close to 1 that we might as well call it 1. It's not 99%. It's 99.999% and then some. It's really close to 1, so I think it's definitely any random score is pretty much going to be below 85. I've got a couple other things I want to do with this example, so I'm going to leave that up there. Just make sure that you can get your calculator to tell you that this is equal to this. And if you want to label these for your notes or for your work or whatever, LB for lower bound, UB for upper bound, and of course the plain old symbols. The more you write them, the easier they are to write. Mu and sigma. So for part C, we're going to again use this distribution of test scores and find the 90th percentile. So we haven't really done this yet, and we're going to learn a new function on the calculator too. It's in the same menu as the other one. I'll show you the name in a second. But the 90th percentile is, if I draw my curve, 90th percentile is where 90% of the scores are less. 90%. That's most of them. So somewhere over here, the picture doesn't have to be great. We're using the calculator to get the value. I'm going to call it P90 for the 90th percentile. And it's a test score. It's not a probability. This is P for percentile, not like the probability function. Let's see. So if this is 0.9 or 0.90, whatever, that's the area to the left of the P90, the 90th percentile. That's the value that we're looking for. The book enjoys calling this number K. It doesn't have much meaning just as a constant, but it is quicker to write than P90, so you might like K also. But this is a different function. It's called the inverse normal function. As I said, it's in the same menu location as the normal CDF calculator function. It looks like this though. INV norm. And the inverse norm function has first the area to the left. Area to left. Always to the left. If you have the area to the right, you can get the area to the left just by subtracting it from 1, but it's got to be the area to the left for the inverse normal input. And then the mean and the standard deviation. I'm going to label those two. You can see where they come from, but the first is the area to the left of the value. The mean and the standard deviation follow, and what this is going to give me is, in this case, 69.4. And that's it. That's a test score. I don't want to write it here, but this is the K that we just found. The test score for which 90% of the test scores are less than. That wasn't great grammar, but I think you get the idea. In other words, my summary here would be P90 equals 69.4. The 90th percentile is 69.4. I've got another one of these inverse normal examples. For part D, find the 70th percentile. So I'm going to go through pretty much the same steps, drawing my normal curve. I know 63 is in the middle. That's not really what I'm looking at here, though. I'm not talking about a score of 70. I'm talking about a score where 70% of the area is left of it. And that has to be over here. Here's 50% of the area is to the left because it's a symmetric distribution. But over here somewhere is P70, or K for the time being, but it's the 70th percentile. And to find that K value, it's the inv norm function with the area to the left, which is 0.7, 70%. You can see it, the 70% a little bit better like this, but the area is what I put in here, not the percentage, not 70, but 0.7. And then the mean and the standard deviation. And I hit enter once I've got that entered, and it gives me 65.6. That's probably a pretty good location for it. The area to the left, I didn't shade it initially because I labeled it, but that's the shaded area now to the left. That is a score of 65.6. You can see it's a greater number than the 63, of course, because it's to the right. But that's the 70th percentile. Okay, so I have another example that's going to demonstrate a little bit different use of the normal CDF function. This is example 6.9, and I don't want to write the whole thing up there. I'm going to read it and just summarize. So it says a personal computer is used an average of 2 hours per day for entertainment. Assume that personal computer entertainment use time is normally distributed with a standard deviation of 1/2 hour. So that's kind of hard to follow from a verbal description. And they put it like that intentionally. They put it as sentences. What they said there was that the mean, the average use is 2 hours. That it is normally distributed. That's important. If we don't know it's normally distributed, it might not be, but they're saying that. And then the standard deviation is 1/2 hour. I'm going to say 0.5 because we're typing things into the calculator. It's easier to type a decimal than it is to type a fraction. So to start, I want to describe the distribution of the random variable x. Actually, before that, what is the random variable x? Well, it's an average PC. An average PC. It's a randomly selected PC. So the number of hours a random personal computer is used for entertainment. And I can summarize this information using the notation x is distributed normally with a mean of 2 and a standard deviation of 0.5. And that's kind of the whole story here. We can use that in the calculator functions to answer these questions. So that's some important context. That's the actual information we're working with. But it's all right here. So the first question is to find the probability that a random PC, randomly selected personal computer is used for entertainment. Don't climb that. Stop climbing that. Between 1.8 and 2.75 hours. And this is different than what we saw before. We saw less than a certain value for those test scores and greater than a certain value. Here it's between two values. And this is another place where the picture really helps. I'm going to sketch this as a normal curve with the mean is in the middle. I know that's a 2 that was given. But between 1.8 is a little bit to the left. And you don't have to get it really, I mean, if it's too close, it's hard to read the individual numbers, but I think this will be okay. And then 2.75 is greater than 2, so it's to the right a little bit. And this is the region that, the region for which I'm going to calculate the area. That is the probability. I think, let me put this up here. So it's distributed normally with a mean of 2 and a standard deviation of 0.5. Here, I'm going to use the probability notation first to kind of further organize what I'm about to ask the calculator. You can go straight from this, but I'm trying to find the probability that x is between 1.8 and 2.75. And that probability notation kind of sets me up a symbolic picture of the graph. The area between 1.8 and 2.75 is the probability between 1.8 and 2.75. The value of the variable between those numbers. The shaded area between those numbers. To find that, I'm going to do the normal CDF. And the normal CDF is the function that's going to give us the probability. The inverse normal was the one that gave us the score, or the data value, not a probability. This one is going to give us a probability. I need my lower bound of 1.8, my upper bound of 2.75, my mean of 2, and my standard deviation of 0.5. So those are the 4 inputs. Remember, lower bound, upper bound, mu, and sigma. Mean and sigma. And do practice drawing the mu and sigma. We're going to use them a lot. Not just x bar. X bar is another way of saying mean, but this is the population mean. And that's going to give me the following number. 0.5886. And that's what you should get when you find your normal CDF function in your calculator, put in the appropriate numbers, you should get exactly that number. And I've got another example that comes off of this. Really, I'm going to draw a new picture. But the only thing I need to bring with me is that, well, we know it's normal, but the mean and standard deviation are the 2 parameters that I need. So for part B, find the maximum number of hours for the bottom 25% of PC entertainment. So abbreviating a little bit here. The bottom 25%. We want to find the number of hours. So the average, the mean, is 2. We're looking at something below average. So let's get a figure, a graph to organize this. Remember, the mean is in the middle, that's 2. And I want to find the data value along the x-axis where the area to the left of that value is 25%. What we're finding, I'll label it. It's over here somewhere. That's the K value. If you want a quick way to write a symbol for it, it's also the 25th percentile is that value that puts an area of 0.25 over here. 25%. This, of course, is 75%. The upper 75%. This is the lower 25%. P25, the 25th percentile, is the value that cuts or divides that lower 25 from the upper 75. There's another name for it, though. And we studied this months ago. That is Q1, the first quartile. Same number. All right, now to find this, I don't want to erase that. Yep. That's fine. I don't need that. To find this thing, to find my k, I'm going to use the inverse normal function, inverse inv-norm, and it's pretty much set up for me. The area I want is that 0.25. That's the area to the left. Area to left. The mean is 2 and the standard deviation is 0.5. And what that comes out to is 1.66 hours. And what it means is that 25% of personal computers are used for 1.66 hours of entertainment on average per day. So it's kind of the cutoff between the bottom 25% and the top 75%.